So looking at the hypothesis test for the difference between two proportions, what we're looking at is to see if there is a difference between the two groups. If the difference is 0, that means the two groups are equal. There's no difference between the two groups. This is going to be our null hypothesis all the time. This is our assumed truth, and we will always write it. Let me highlight this part. Sorry. This is our null hypothesis. And so we write it as HO P1 minus P2 equals 0. So there's no difference. The two groups are the same. Or, and this is the way I tend to write it, HO states that P1 equals P2. They are the same. Our alternative hypothesis is then going to test whether the difference between these two proportions is less than, greater than, or different from 0. So the alternative will say that either P1 is less than P2, P1 is greater than P2, or P1 is not equal to P2. Those are the three possibilities for what the alternative would say. So we assume that the two groups are the same. There's no difference between the two groups. And then we're going to test, does the first group have a smaller proportion than the second, a larger proportion than the second, or just a difference between the two groups? So the test statistic for this hypothesis is below. The z-score for the difference between P1 hat and P2 hat is P1 hat minus P2 hat divided by the square root of P hat times 1 minus P hat times 1 over N1 plus 1 over N2. So some reminders. P1 hat is the sample proportion of group 1. P2 hat is the sample proportion of group 2. P hat is the pooled sample proportion. So it's the overall sample proportion. N1 is the sample size of group 1. And N2 is the sample size of group 2. So before we get into a test, there are two conditions that must be met. The samples must be independent of one another, and the two samples individually must satisfy the central limit theorem for proportions. When we complete the hypothesis test, we are going to follow the same steps that we would as if we were doing a hypothesis test for a single proportion. So we had 4 steps to follow. We're going to follow those same 4 steps. But we're going to get a little bit of help with steps 2 and 3. Because we can write out this equation, and this equation is actually not terrible. but we don't want to mess anything up. So we're going to do a little bit of this by hand, and then we're also going to use some technology to help us. But let's take a look at the example that I have here. In a clinical trial of Nasonex, 3,684 adults and adolescent allergy patients were randomly divided into two groups. The patients in Group 1, the experimental group, received 200 milligrams of Nasonex, while the patients in Group 2, the control group, received a placebo. Of the 2,013 patients in the experimental group, 547 reported headaches as a side effect. Of the 1,671 patients in the control group, 368 reported headaches as a side effect. Is there significant evidence to conclude that the proportion of Nasonex users who experienced headaches as a side effect is greater than the proportion in the control group at the alpha equals 0.05 level of significance? So this is a controlled experiment, so we want to know, does Nasonex cause headaches as a side effect? Should we be listing that as a side effect on Nasonex? So let's see, we had 3,684 patients in total. Group 1 was the experimental group. Group 2 was the control group. There were 2,013 patients in the experimental group. Actually, I'm gonna shake this up a bit. I'm gonna do some different colors. Group 1 and Group 2. Okay, the experimental group, which is Group 1, had 2,013 patients, and 547 of them reported headaches. Group 2, the control group, had 1,671 patients. 368 of them reported headaches. Is there significant evidence that tells me I'm going to do a hypothesis test? The word proportion, that tells me I'm looking at a proportion. Nasonex is greater than control group. And then 0.05 level of significance. Lots of things to unpack here. So we have an overall, oh, let me make my pen bigger. We have an overall N. We have N1, N2, X1, X2, and alpha. So our overall N is 3,684. N1 is 2,013. N2 is 1,671. X1 is 547. X2 is 368. And alpha is 0.05. It's a lot to get through, but I've got it all summarized. I've got everything highlighted that I wanted to highlight. So the first thing I need to do is write down my null and my alternative. So every hypothesis test, no matter what I'm looking at, starts with an HO and an HA. So the HO is going to be the same no matter what two groups I'm looking at. It's going to be that group 1, P1, is equal to P2. So we're going to start out by assuming that the proportion of patients that got headaches from their medications were the same. And then we want to know is P1 greater than P2, where 1 is the experimental group and 2 is the control group. And I've been consistent about putting 1s next to all the numbers for the experimental group and 2s next to all the numbers for the control group. Step 2 is our test statistic. Now I'll go ahead and show how I would fill all of this in, but I'm not actually going to do the calculation. But I'll go ahead and fill it in. So a few things that I need P hat, I need P1 hat, and I need P2 hat. So P1 hat is 547 over 2013. Okay, I did not give myself enough room. Oh no, I did not want you to come with me. P2 hat is 368 over 1671. So let's figure out what those are real quick. So 0.2717 and 368 over 1671 is 0.2202. So it definitely looks like P1 is bigger than P2 from the samples, but is it bigger enough? Remember, we need it to be significantly bigger. And then the overall P hat is 547 plus 368 over the overall N, which I was nice enough to get, 3684. But the 3684 is just 2013 plus 1687. So that's 915 over 3684. So that's 0.2484. So overall, this is the proportion of both groups that reported headaches. So now the test statistic is a z-score. And I'm running out of room, so I'm not going to rewrite it. I'm just going to plug in the numbers. So it's 0.2717 minus 0.2202. That's what goes on top. We're looking at the difference between these two numbers. And then on the bottom, it's the square root of 0.2484 times 1 minus 0.2484 times 1 over 2013 plus 1 over 1671. And all of this is inside the square root. And then all of this is underneath the division. So not terrible, but not something I really want to do. So here's what I'm going to do. I'm going to pull up a website that you should have access to called Statistics Calculators. This was made by a wonderful professor who is just fabulous. And I came to her and I said, we need a way to do these calculations so that anyone can do it no matter what technology they have. All they need is internet. And she made this website and it's wonderful. So we are doing a z-test for the difference of proportions. So that's the one I'm going to click on. There's also the z-estimate for confidence intervals, which we will do later. So I'm going to zoom in on the top so that we're focused there because we're doing the hypothesis test. Now, input method, number of successes or sample proportions. So if I was given p hat 1 and p hat 2, I could put in the actual proportions. Or if I was given the number of successes, I would put those in. In this case, we were given the number of successes, and that is the more accurate way to do this. So that's what I'm going to put in. So the number of successes for group 1 is the 547 patients that got a headache. And the sample size for that first group was 2013. 13. The number of successes in group 2 is 368. And the sample size of that group was the 1,671. Our alpha is 0.05. And then this was a right-tailed test because it was P1 greater than P2. I can go back to that real quick. So right here, greater than, this is a right-tailed test. So I've put in all of the information that I was given. And when I hit perform hypothesis test, it's going to calculate the test statistic and the p-value for me. So here's my pooled estimate, 0.24837. That's what I calculated for the overall p-hat. My test statistic is 3.60212. The critical value, we are not focusing on the critical value method. Remember, we're only focusing on the p-value method. And then our p-value is 0.00016. And I'll go and explain how we got this in a second. You probably already know, but I'll still write out how we got that. So our test statistic using this formula is I'm still on a highlighter. Okay, here we go. 3.60212. And then we also got the p-value. And the way that the p-value was calculated was from 1 minus norm.s.dist 3.60212, comma, true. And it's 1 minus because it's a right-tailed test. So that's how we got the p-value, 0.00016. So we're almost done. Conclusion and interpretation So the big question we have to ask is our p-value less than our alpha? Our alpha was 0.05. Yes, it sure is. So if our p is low, we reject our null hypothesis. And then our interpretation. There is enough evidence or sufficient evidence to support the claim that the proportion of Nasonex users reporting headache as a side effect is higher than the proportion in the control group. And now the manufacturer can take this information and decide maybe we need to report headache as a side effect. Sounds like a good idea. So there you go. That is how you do a hypothesis test for the difference between two proportions.